Right, okay, here we go. So this is the last bit of matrices on chapter 6. I'm actually going to use it today for actually solving some maths problems and possibly even some sort of relevant stuff to sort of real life applications. Okay, and we're going to solve some simultaneous equations. I'm going to start just with two unknowns. So a classic linear simultaneous equation with two unknowns. I'm going to start with the answer and work backwards, and let's hopefully see what we get. So I'm just going to say, okay, let's say x was 1 and y was -2. So I'm just going to generate two equations here. So solve 2x plus y, or 2x plus y will equal 0, and 3x minus 2y will equal 7. These are our answers. I imagine you wouldn't be told the answer. But that's obviously what we're trying to get to. Now, there's different ways of doing this. You'd probably go for elimination maybe here. You could substitute. Or we can now use matrices. And you wouldn't use matrices for a 2x2. But hopefully you'll see in a minute why if you have 3 unknowns or even 4, matrices are really, really powerful. So I can rewrite this in a matrix system. Okay, so I can rewrite this in a matrix system. So what I mean by that is, well, how can I write this? Well, you can probably see that this is going to be the same as 2, 1, 3, minus 2, all multiplied by x, y. And that will equal our answer, 0, 7. Let's just see if that works. If I do the top row, so 2x plus 1, y equals 0, and I get the same on the bottom, 3x minus 2y equaling 7. So that's just a different way of writing that set of simultaneous equations. Okay, so I can solve this. So in general, I suppose, if I've got an equation, so let A equal this matrix, this system matrix, then obviously A x y equals some vector. I'm just going to call that the answers vector A, the answers matrix V, which is just, let's call that V. Therefore our solution, if I times both sides by the inverse of A, remember I've got to get the order right as well, xy will equal the inverse matrix times the answer matrix there. I'm going to use that to actually answer this question. Okay, so I've got this system, let's rewrite it. So 2, 1, 3, minus 2, x, y equals 0, 7. Now, if I say, yeah, A equals 2, 1, 3, minus 2, I need to work out the inverse of A to the minus 1. I can do this on the calculator, or I can do it longhand. For 2 by 2, it's not too bad. The determinant of A is going to be minus 4 minus 7. So the inverse is 1 over negative 7. You flip those two, so flip these two, and you flip the signs of the leading of that diagonal, minus 3, minus 1. Okay, so that's the inverse. And then all I need to do to work out xy, so xy is quite simply the inverse, which is minus a 7th, minus 2, minus 1, minus 3, 2, multiplied by that vector we had on the right hand side, which was our answers to that solution. And that should give me the answer. So if I work this out, minus a 7th, that's going to be that's minus 7 on the top, and then on the bottom 14, which quite nicely equals 1 minus 2, and then I can compare the elements. Therefore x must equal 1, y must equal minus 2, which was what I had at the very start. So it's quite a nice way of solving this. Again, you might think this is really long-winded, but you can see that it's quite easy for a computer to maybe program. And also you'll see with 3 by 3s in a minute. that it does become a bit easier. Okay, let's look at 3 unknowns this time. So a simultaneous equation with 3 unknowns, and you could be asked to solve minus x plus 6y. And it could even ask you using a matrix system or a matrix approach, and then you would be forced to use a matrix approach to get the marks in an exam. So we're trying to find out what x, y, and z is here. Okay, there are different ways of doing this, like I could number the equations and eliminate them one at a time. Or I can do it using a matrix system. So the matrix system would look like this. So it's minus 1, that's 6 minus 2. These are the coefficients in front of the variable, the unknown, sorry. 5, and then if we would have to multiply that simply by x, y, z. Again, you can check it if you don't believe me. That will work. 21 minus 16, 24. So you set up this matrix is the coefficients. Okay, so we need to do the same again. We need to work out the inverse of that 3 by 3, and luckily for these sort of equations, your calculator is fine to do that. So let's just do a 3 by 3 minus 1. If you want to do a bit of practice, it's good to be able to do that anyway. 6. Okay, so that's my matrix in there. I can clear that, remember. I go option, mate, then I have to use that button there, and it will give me the matrix. So the inverse is, so x, y, z is going to equal that inverse, which is 1 over 27, 4 minus 2. It's all over 27, so I'm going to put 1 over 27, and it's 1, 4 minus 2, 1, 4 minus 2, 4, 1, 1, 4, 1, 1, finally 10, 13, 34. Oh, that's over. Oh, that's over 189. Okay, 10 over 189. It's horrible numbers here. 10, 13, 34, and 34. These, annoyingly, all over 27 now. And I, at this stage, need to multiply that by 21 horrible numbers here. 24. Okay, again, I'm going to do this on the calculator just because they're horrible numbers. I'm going to store that matrix as A. I can do that. If I want to define a new matrix, matrix B, number of rows 3, number of columns 1, minus 16, 24. Okay, and I'm going to do matrix A multiplied by matrix B, and I get an answer minus 142 x, y, z was minus 142. At least that's nice numbers. I'm just going to check it in one of these. Let's maybe check it in the top one. So you've got 1 plus 24, which is 25 minus, that does work, doesn't it, for the top equation? I should be diligent and check it with all the equations, but there you go, and I should really write this as my final answer. X equals minus 1, y equals 4, and z equals 2. So it's quite a nice method for solving simultaneous equations, because it's very systematic. Okay, right, now types of solutions. Now you may have found, we'll have a look at, so types of solutions when you've got 2 unknowns. So when you've got two unknowns, something like x plus y equals 7, and then maybe 2x minus 3y equals 6. These are equations of lines, aren't they? So you've got two lines there, and two lines can do two things, and it's in the two-dimensional plane. So the most likely case, these two will cross at a single point. Got two straight lines, most likely they will cross at a single point, but they could be parallel. They could be parallel, and therefore no solutions. Yeah, or they could be the same. They could be the same, and therefore infinite solutions. So those are the possibilities, okay? And you can work out these quite quickly, because if you create the system here, so if we the matrix here, the system matrix would be that. If the determinant of that, so if the determinant of that matrix equals does not equal 0, it will cross at one point. Okay, and we call that consistent system. A consistent system. And that's the most likely case, isn't it? If you draw two random lines, it's most likely they're going to cross. But if it does equal 0, it could be well, if it is equal to 0, i.e. it's a singular matrix, remember the determinant, it's a singular matrix, it will have no inverse, it doesn't have an inverse, and therefore could be 1 or 2, okay? No, sorry, 2 or 3. So it could be parallel, or it could be the same with infinite many solutions. And you'd have to have a look at the equations. I mean, it's pretty obvious if they're parallel, they'll just be multiple of each other, and if they're exactly the same, sorry, if they're exactly the same, they'll be exact multiple of each other, whereas if they're parallel, it's that constant at the end might differ. But you have to go back and check that. But because, as I say, mostly they'll be consistent. And these are called the no solutions is an inconsistent matrix. And this one is consistent because it does have solutions, but it has infinitely many solutions. So consistent means solutions, inconsistent means none. Right, let's look at we're going to look at the a three unknowns case now. So three unknowns, types of solution. So three unknowns, similar to what we just looked at. So if you've got something like, I don't know, anything at ax plus by plus cz equaling d, okay? Now, this is not a straight line anymore. We're going to do more on this when we do the vectors chapter later on. But whenever you see an equation like this, these are planes. This is the equation of a plane, which is basically a 2D rectangle shape that goes on forever in space. Okay, so those are equations of planes. I'll explain why that's the case when we do the vectors chapter. Okay, but they are, yeah, it's basically you're adding a third variable, which means you're adding in an extra dimension to your straight line, which makes it a plane. So, like we had with straight lines, there's only really three possibilities with straight lines. They're either cross, they're either parallel, or they're the same. Planes, there's a few more options. So if you've got three planes, you've got three systems. There was only two lines because there was two equations. Here we've got three planes. Three planes can either now please refer to page 118 here from the textbook, because the diagrams are much better than I can draw. So planes here, they can either meet at one point, and again you might think, just to visualize three planes, they can meet at one singular point. Again, if you look on page 118, it will show you that. And this is the most likely. Most likely, if you were to pick three random planes, the most likely thing is they would meet at one point. Now that means there's just one set of solutions. Okay, there's one value of x, one value of y, one value of z, which satisfy it. It also means it's a non-singular system, which means the determinant will not equal 0, which is useful. And we call this a consistent system of equations because there is a solution. Consistent system of equations. So you need to know what the term consistent means, which means there are solutions. You need to know what non-singular means, which means that it does its determinant does not equal 0. Okay, so that's the most likely case, but you'll see that there are other cases as well. Okay, and this is so if the determinant of the system matrix equals 0, then it could be a range of things. Okay, that basically there isn't a singular solution. So if the system of matrix equals 0, then either it could form a sheaf. Now a sheaf is where it forms it forms a straight line. Okay, it forms a straight line, so it's got infinite solutions because it's all along that straight line. So therefore it is still consistent because it has a set of solutions and it has an infinite set of solutions, so it's a consistent system. And it has infinite solutions there. So that's option one. It could be that. It could form a triangular prism, which has no solutions, and is an inconsistent system because it has no solutions. Okay, and the other two, it could form two or more planes might be parallel. I mean, these are very unlikely, but they're possible. So two or more planes might be parallel, and therefore there'll be no solutions. You could have two parallel and one crossing through both, or all three parallel. So no solutions and inconsistent. Or finally, you could have all the planes are exactly the same. So all planes exactly the same, and therefore infinite. That will be consistent because there is infinite solutions there. Consistent and infinite solutions. Luckily, case number 1 is the most common, but case number 2, like if you work out the determinant is 0 and therefore there's no inverse, so there isn't a single set of solutions, it could be 2, 3, 4, or 5, and you might be asked to find out which one that is. Okay, it might ask you what will this system of solutions look like? What will it form? Okay, and we're going to do an example of that. So this is example 22 from the book, but I'm just going to go through it hopefully a bit more slowly so you can see what's going on. So we've got a system 3x minus ky minus 6z and equals k equals 2 and okay, so we've got that set of equations and planes, and it says solve the equation when k equals 0, when k equals 1, and then when k equals minus 6, and it says solve it if you can. If you can't solve it, then tell me what sort of system it will be. So is it one of those 5 options? Okay, now we'll start with when k equals 0. So what if k equals 0? My set of systems is going to be 3 minus 6 It's going to be 0x, 3y, 3z, minus 3, minus 1, 3, x, y, z equals 0 to minus 2. And I'm going to do this on the calculator again. I'm just going to go, I'm going to go to define matrix. I'm going to put in 3, 0, 6, 0, 3. Okay, so that's my new matrix here. Now I'm going to do a check. First of all, with all of these, I'm going to check the determinant. Now, if the determinant is positive, I know there's solutions immediately. So let's just do that immediately. And I can do that by longhand, or I can do it on the calculator. So I check the determinant, minus 18. So it does not, it's not equal to 0, therefore I know it's option 1. There's a single set of solutions. Okay, and the best way to do that is, remember, x, y, z equals, if I call that matrix A, it would be a to the minus 1 times 0 to 2. And I can do that. Again, you would expect to potentially do this longhand, but I'm going to do it on the calculator fairly quickly now. So I'm just going to define a new matrix, matrix B. It's got 3 rows. Column 0, 2, minus 2. And then to get that, I go option mat A to the minus 1 times by option mat B. And it does give me 4/3, 0, and then 2/3. And that basically has solved the set of systems for me. So x equals 4/3, y would equal 0, and z would equal 2/3. And that's my answer when k is equal to 0. Okay, so the next option was when k is equal to 1. So when k is equal to 1, this time my matrix is going to look like 3. It's going to be 3, 1, minus 6, 1, 3, 3, minus 3, minus 1. X, y, z equals 1, 2, minus 2 this time. Okay, so I've got a different set of equations here. With a potentially different result. But I'm going to do the same again. I'm going to check the determinant. I'm going to check the determinant first. I do need to edit my matrix here. So I can go back in here and go option. I can edit my matrix A. And I can make that, just change those zeros into ones. And the rest I think should be the same. That's good. So that's saved now as mat A. So if I go to option determinant at A, and it's, oh, I might have made a mistake there somewhere, because that should be minus 1. In fact, that should be a minus 1 there. So I have made a mistake. Have I made any others? No, that should be a minus 1 because I know that so I need to just go in and edit the matrix. Make that minus 1. Zero. Okay, so I get 0, and in this case, if I call this matrix B, the determinant of B equals 0, and I'm a bit annoyed because it's unlikely to equal 0, and that means it could now be any one of those 4 options. It could either have an infinite solutions, it could either have triangular, so no solutions, or it could be the same, and so on. But I have to do this with traditional methods now. So I have to go back in, and I'm afraid I can't use the matrix really anymore to help me, which is frustrating. As I say, in reality and in real life, you would nearly always get a set of planes that intersect at one point. So I now have to look at this and I have to sort of say to myself, okay, so I'm going to rule out, basically I'm going to label the equations. And I'm going to go back to my system here, my options here. So option 5, all the planes are exactly the same. So are they all a multiple of each other? So they're definitely not a multiple of each other. So I can rule out option 5, all planes the same. All planes the same. Well, absolutely not. I can rule that one out completely. Option 4, I'm sort of going to work backwards here. So option 4 are more than one plane the same. So more than one. More than one plane parallel. Okay, so are more than one of the planes parallel? Well, I can do that by, well, are they a multiple of each other? No, they're not, are they? There's no equations there that are a multiple of each other. They're certainly not all the same, but likewise, they're certainly not all a multiple. One of them is not a multiple of any of the others either. So absolutely not. It's not going to be that one either. Point number 3. Now, are there solutions here? So those are the two to look out for really quickly, if there's any parallel. But now the two that often come up are the triangular one or the sheaf. And you've got to eliminate. So for these next two, you must then eliminate one unknown in two different ways. The best thing to do here is to look at an example. So I'm going to eliminate Z. So I'm going to eliminate Z using equation 1 and 2 to begin with. So 1 and 2 means to eliminate that, I'm going to have to do equation 1. To get the Z's the same here, I'm going to times the second equation by 2. I'm going to just add 2 times the second equation. I'm going to do it in one step and be really careful I don't make silly mistakes. I'm going to get 5x. If I times that one by 2, I'm going to get plus 5y. The z's will disappear, and that's going to equal 5. I'm going to call that equation 4. And then I'm going to do the same, eliminate z using, so eliminate z using equation 2 and 3, 2 different ways. So 1 and 2, I've used all 3 equations, and these are really easy because I can just do 2 minus 3 because the z's are already the same. So if I do 2 minus 3, I get x. Oh, that should be an x there. So it's going to be 4x plus 4y equals 4. I'm going to call that equation 5. And then I attempt to solve these 2 equations, okay? So these 2 equations here, if I solve these 2, you will see, so basically, in both 4 and 5, you'll see that they're the same equation. X plus y equals 5. Therefore, there is infinite solutions. X and y can be anything because they satisfy both those equations. So there's infinite solutions. Therefore, the 3 planes form a sheaf. Okay, so the 3 planes form a sheaf. Okay, there are infinite solutions there. X and y can be anything, which means then z, whatever z is, x and y can be anything regardless of the value of z. Right, let's look at the third case, which was final bit, which is when k was minus 6. So see when k equals minus 6, and we get this we get this set up. What was that mean? Minus 6. 2 minus 2. Okay, so if I call this matrix this time C, and if I work out the determinant of C, you can probably predict what this will be. In fact, I'll tell you what it will be. It is 0. You can check me, but you can test yourself, but it is 0. So again, you're thinking, oh no, it could be one of those 4. So let's look at the equations. So we've got 3x plus 6y minus 6z. Minus 6x plus 3y 2. Okay, so we've got three equations there. Are any a multiple of each other? You've got to look carefully here. You think 1 and 2 are close, but they're not quite. So they're certainly not the same plane. No good. 4 and there's no 2 there that are parallel, so they're not. There's no parallel planes. So you can rule that one out. To be honest, you can usually rule those 2 out. So it's now just determining whether it's a sheaf or a triangular prism where there's no solutions at all. And we'll do the same thing. We'll eliminate Z again using the equations 1. So if we use 1 and 2, we're going to eliminate Z. Again, it's going to be the same. It's going to be 1 plus 2 times equation 2. So it's going to be, if I do that, I get minus 9x, get plus 12y equals negative 2. Okay, and then if I use 2 and 3, let's call that equation 4. I just need to minus them again. So 2 minus 3, I get minus 3x plus 4y equals 4. Equation 5 there. Okay, now if I try and solve these 2 equations, so if I multiply the bottom one maybe by 3, so I've got equation 4 here, and then I've got 3 times equation 5 underneath. You can probably see what's going to be the problem here. If I minus the equations, I end up with 0 equaling minus 14. Well, that's clearly not true. And if that's not true, then therefore no solutions and the 3 planes form a triangular prism. Okay, so basically you have to solve it a little bit old school. If the determinant is 0, you have to eliminate one unknown using both equations in a different way. Okay, right, appreciate that's quite a long video, a lot to take in there, so do take your time to digest it. I do want you to do a few questions on this though, please, and it's page 120, exercise 6F. I want you to do questions 2 to 6 inclusive. Okay. And this is the end of matrices. The next lesson we'll just be doing some practice on the mixed exercise. But well done, another chapter complete, and I'll see you next time.